Okay, so it's my pleasure to open this workshop, which is the second workshop of ASAP. So as you know, ASAP is a project dedicated to developing AI algorithms for the future onboard use on space missions for tasks such as selective downlink. So we have a broad range of talks also and related to this topic, but also general AI topics in space plasmas. And yes, so we have topics on hardware, on AI algorithms. Yeah, and it's my pleasure that this workshop is taking place at KU Leuven. And it's my pleasure to welcome the first keynote speaker, Enrico Camporeale, who is a professor at Queen Mary University, London, and also has a position at University of Colorado. Yes, so the floor is yours.
All right, thanks, George. Well, thanks for the kind invitation. It's a pleasure to be here. It looks like, looking at the schedule, looks like a very interesting day ahead of us. So I'm very pleased to give this talk, which some of you might have seen bits of it. It's a kind of talk which has been built over the years, but yeah, I have way too many slides, so I guess I'll just get started with the. I hope. Kind of a small preamble that you might or might not be familiar with, depending on how much you paid attention to certain things. Okay, the title is "We're Living in Strange Times." So this is the archive. I mean, there's this usual argument that you all know that machine learning is growing, and there's a lot of publications. I myself am with AGU, so this is a plot of how many AGU publications with the keyword machine learning over the last 5 years, 2 years, 1 year, and 6 months. It's growing. Number of machine learning in physics in ABS, it's growing as well. What it's a bit worrying to me is that if you look at the archive preprint, I mean, you're all familiar with archive, in the machine learning section, so this is the snapshot from last week, right? And there were 1,600 papers in a week. So this amounts about 80,000 per year, right? Obviously, everybody understands that that's not a healthy number in any field, because out of these 80,000, 79,000 will just be useless, to be completely frank. And for sure, there will be very important and breakthrough papers, but the problem is it's hard to understand what is good and what is not when you have to sift through 80,000 papers per year. So this is one situation we're living in now. So obviously there's a hype in machine learning, I believe. I mean, somebody says there will be an AI bubble and then it will settle down. So probably if we have ASAP 2 in 5 or 10 years, this number might or might not be lower. On the other side of the spectrum, there's space physics. Many of us live in the space physics arena, and that's what we call home, academically speaking. I think this is the opposite problem, right? Because here we have 12 papers in a week. So my personal conviction is that space physics has been plateaued now for many years, or maybe even decades. And because again, I mean, the same argument is true. Out of these 12 papers, maybe 1 is important, and 2 and 10 not so much. So the field has been plateaued, and there haven't been many breakthrough lately. And that's what I think there is really an opportunity to combine, and that's I guess what most of us work on, to combine AI and machine learning and space physics. So I don't mean at all to say that space physics is dead or is going to be in bad shape in the near future. There's a lot to do and to discover, but we need to be able to evolve as a field. And one possibility, probably not the only one possibility is to combine machine learning and space physics. Okay, there's this idea of data science as the fourth pillar of the scientific method. This is not my idea. In fact, it's been around for some time. If one wants to attribute this, I guess credits go and be small to Jim Gray, which was a scientist at Microsoft that suddenly passed away, tragically, actually. And this was from 2009 when he published his book, The Fourth Paradigm. Now, a little bit of my own kind of advertisement and a little bit of self-credit. So myself and a number of other people, you might be familiar with this, created a journal because there was sort of a niche and a vacuum in the publishing landscape, especially in AGU. We created a journal called JGR Machine Learning and Computation. And this was sort of the editorial we published at the very beginning of the journal. This is now almost 2 years ago, where we set up the guidelines and we explain why we need this journal. And again, we repeat this idea of data-driven methods as the fourth pillar of scientific discovery. The other three, I guess you're familiar with, is experimentation, theory, and computations. And then something we are very proud of, so this was before the Nobel Prize, but we had this argument that said that this new paradigm is obviously not restricted to geoscience, and we made the explicit example of AlphaFold. Obviously, somebody in Stockholm read this one and decided to award the Nobel Prize to John. So this was before it was awarded, so kind of proud again of foreseeing this happening. Okay, let's dig a little bit more into. Again, I believe most of the people in the room and online might be familiar or not with those concepts, but just to be on the same page, it's kind of a loose taxonomy of machine learning in science. So essentially, the way I see it, there are two distinct categories / objectives and goals to use machine learning. So one is to use it to do inference, prediction, forecast, and this comes in the form of creating surrogate models or in other computational areas of physics or science. Those might be called reduced order models. And the goal here is really to devise a model that runs faster than a baseline, right? Your baseline can be an empirical model or a physics-based model, but you really have to play the game of kind of a trade-off between accuracy and speed, right? Neural network are expensive to train, but then they run very fast. Neural network is sort of the king of machine learning nowadays, but obviously it might not be as accurate as other methods. So this is the game you wanna play. Another goal for this inference / forecast is to do a forecast of the output of interest. So I'm going to talk specifically about space weather. Something to keep in mind, which oftentimes is forgotten, is that this applies very much to space weather. Understanding is neither necessary nor sufficient for prediction. This is the typical criticism that people make when you apply machine learning. Say, well, but you don't understand anything about the physics. Well, it doesn't matter for this particular case. You know, if it makes a good prediction and it's reliable and so on, that's all you need. Another completely different arena where you can apply machine learning is data-driven discovery of models. I have a few examples later. And for instance, you can use a machine learning AI to discover new physics from the data, possibly in an intelligible way, so that you actually discover new knowledge, make new knowledge. Or I have an example that finds some new parameterization of some missing physics in models. I mean, all models we use in physics are approximations to an extent. There are some missing physics. They usually is fed into through some fine tuning of the many knobs you have in your model. Think of MHD, for instance. All right. Okay, so this is not a review talk because that would take the whole day, but I just try to just give an example and try to fit as many papers as possible in a slide, just to show that the literature really is exploding when it comes to using machine learning for space weather. And this is, as I said at the beginning, a good thing and a bad thing, because one always has to understand how is so many papers, what is good and what is not. Wind forecast is an obvious topic in space weather. radiation belt fluxes, lots of papers from different groups on this topic. Solar flares is possibly the one topic which I've seen the most publication in machine learning for space weather. I haven't counted, but possibly more than 50 or even 100 in this particular topic. Mass ejection, try to estimate the arrival time of CME and then all the geomagnetic disturbances, geomagnetic indices. I've done a few works in this topic myself. Neutral density estimate. This is very important nowadays for the exploding numbers of satellites in LEO, low Earth orbit, and the increasing chance of them colliding and making a mess of debris. So one needs to be able to estimate the neutral density and the trajectory on low Earth orbit. So the bottom line really, and I'm going to become a bit more technical now, but the bottom line sort of preamble here, in the last 5 years or so, maybe even, no, I would say 5 years, machine learning has literally been applied to any task in space weather forecasting. And that's why, making now a review, I wrote a review paper, I'm going to mention it in 2019, so now more than 5 years ago. That is pretty much out of date now, and somebody else maybe should write a new review paper. But it's a daunting task because there are so many works out there. Typically, a machine learning algorithm claims to be outperforming there is a physics-based equivalent or whatever is the state of the art in that particular forecasting exercise. And it's outperforming either in terms of accuracy, computational cost, or maybe both. And oftentimes, however, one has to be cautious because this is the case when the baseline model typically is weak. For instance, if you compare machine learning model versus a persistence model or a climatology, something which is kind of zero cost, then your baseline is weak, and then it's an easy win, so to say. So some of you in this room and online were a couple of weeks back enjoying the Madrid weather and food, so we're gonna have those talks and presentation. I mean, they're already online, but we're gonna make them more visible for the whole community to enjoy the work. And there were lots and lots of topics, as again some of you that were there noticed. Okay, let me get a bit more technical and to talk specifically about the couple of things that my group, when I was primarily at the University of Colorado at the institute called Space Weather Track, worked on. So in the last few years, we have developed these two engines under the hood, which are kind of mathematical methodologies, which I'm going to explain very, very briefly. One is called ACRU, stands for Accurate and Reliable Uncertainty Estimate, kind of follows the philosophy that a forecast is not a forecast if it's not probabilistic. So the idea is to take a deterministic model and kind of attach uncertainty on top of it. This is the main reference, came out on International Journal for UQ. And then building on top of ACRU, we have ProBoost, which stands for probabilistic boosting. There's unfortunately not a reference yet. It has been in preparation now for months. Maybe at some point we'll manage to publish it. Okay, so this is a bit technical. Of course, you're very welcome to look at to read the paper. This is another paper that came out in Space Weather. We actually it's kind of explained in great detail, but just to give a kind of a general idea, the way ACRU works is the following. Again, you have a deterministic model. Deterministic means that for any given set of inputs, which typically is a multidimensional vector, you always have the same output, right? It's not stochastic in any given way. And it can be a physics-based model, it can be itself a machine learning model, it can be a empirical model, whatever, as long as it's deterministic. Then ACRU, the way I see it, is really a kind of a plug and play methodology that you plug and play on top of your deterministic model, and it transforms your model into a probabilistic model just by, basically, it's a simple example in 1D. If your model gives you this red line as a model output, it attaches an uncertainty, a confidence interval, if you wish, on top of it. the way it does that is that it enforces accuracy and reliability. So eventually you want to have a measure of uncertainty as a function of your possibly the same inputs that your deterministic model takes. So this ends up being an optimization problem. And so reliability and accuracy, I'm going to explain what those terms mean. So the reliability is better described by means of this reliability diagram. It is the property of a probabilistic model that measures its statistical consistency with observation. So you think of a model that, again, probabilistic prediction of rain versus no rain. A model is said to be completely reliable if any time you predict 40% chance of rain, then it rains 40% of the times, right? If you predict 40%, it actually rains 60% of the time. It means that you're underconfident. If you predict 40%, it actually rains 20% of the time, then you're overconfident. So this is an important basic characteristic that you want to enforce on your model to be reliable. Second one is accuracy, which is maybe more intuitive. There are many, many different ways of measuring accuracy. What we decided to do is to use a metric which has actually been used a lot in meteorological and sort of terrestrial weather prediction. And it's called the continuous rank probability score. So again, it's a bit technical, but just to give you a graphical understanding of what it means. So if your prediction is probabilistic, it means that you're not predicting just a single number, but a PDF, right? But let's assume for simplicity that your PDF you're predicting is a Gaussian and it's a black line. So the blue will be the median, which is equal to the mode, which is equal to the mean in a Gaussian. And the red, obviously your model is not perfect, so the red line is the actual prediction, so kind of your ground truth, okay? So what CRPS does is to, instead of working in the PDF space, to work in the CDF, the cumulative distribution function. So the black Gaussian becomes, I mean, all CDFs are sort of sigmoids, or S line, and your single deterministic, your single value, your ground truth, your observation is just one value. So this is a step function, right? So CRPS, in a sense, it's the integral of the different square of these two curves. So it's proportional to this area. And it's a negative oriented score, meaning that it's equal to 0 for perfect forecast. So basically what you want to do is to minimize this area. So these are three examples with the same mean, but different standard deviation for the Gaussian. And this is the value of the CRPS. And you see this is overconfident, this is underconfident, and this is about right. So in this case, the best CRPS for these three cases would be this one. So what accrue does, kind of the recipe, is to, for any given set of inputs, to estimate what is the standard deviation of a Gaussian. So there's a further work of a PhD student at the University of Colorado that actually has extended this into non-Gaussian distributions, but the original paper was for Gaussian. Again, this optimal width, the standard deviation, is the one that optimizes both accuracy and reliability. We have shown that those two characteristics are actually competing objectives. So what you end up with is to define a cost function, which is sort of a weighted sum of the two, and they cannot be minimized simultaneously. So you have to find the sweet spot where those are both small enough. So again, it's a minimization problem. It can be solved in a number of ways, but a simple way, especially in multiple dimensions, is to use a deep neural network. That's what we do. So at the end of the day, we have a neural network that takes the input of your simulation or whatever deterministic model, and for any given point in your input space, estimates what is the standard deviation. All right, so to move on into ProBoost, I have to explain what gradient boosting is, first of all. So this is just gradient boosting in one slide. Some of you might be familiar with it. It's actually one of the most popular and one of the strongest algorithms in machine learning. It is very simple. I mean, its beauty is really, it's very simple. So the idea is to build a hierarchy of models. So assume you want to solve a regression problem where you have some data points. You have your first model. It can be a neural network or decision tree or whatever. This gives you a certain output, right? From that output, you can calculate the residual or the error with respect to the ground truth. Then you can use that residual for a second model, so the residual of the first one will become the target for the second one. And you can do this iteratively in a number of ways. And then at the end, this becomes additive in the sense that you can take model 1 plus model 2 plus model 3, and you can just literally add them together, and this will give you your final model. As I said, one of the strongest algorithms, if you look at the Kaggle competition, for instance, I've read somewhere that 80 or 90% of the winning model are gradient boost. It really underperforms on imbalanced data set. And this is really where we focus on in space weather. Unfortunately, this is an example of a DST, geometric DST prediction. You might be familiar when DST goes very negative, it means that there's a strong storm. And this is a simple application of gradient boosting, which predicts the DST very well everywhere except when it actually matters, right? And this is a problem in space weather. So what we've done, instead of kind of being inspired by gradient boosting by using a crew, we have developed ProBoost, probabilistic boosting. The way it works is the following. So we can use sort of the power of a crew to identify regions in feature space where a predictor works well and where it doesn't. So we start with sort of with the first model or a baseline model, and we compute the uncertainty in feature space, and we realize that for this region in feature space, the uncertainty is too large. And so we work again with a hierarchy of model by subsampling the training set. So if those spaces, if there's a region in feature space or input space where the first model didn't work so well, then the second model will focus on that region. And we can do this iteratively a number of times. And then again, the subsampling criterion is based on the accrue uncertainty that can easily be estimated everywhere. And then at the end, we have this number of models that we need to combine linearly. And the simple rule to combine them is to weight them by their precision, which is the inverse of the standard deviation. So here, the simple heuristic is where the standard deviation is large, means the uncertainty is large, and that model at that particular point is weighted less than others. Okay, as I said, these are the two sort of engines running behind the number of models. So this is LiveDST, which has been, now, I think, for more than a year, maybe even a couple of years, running in real time on the Space Weather Track website. So this is a 1 to 6 hours ahead probabilistic prediction of DST, and the probability comes with the fact that there's a shaded kind of pink area here. Okay, this was a case which wasn't particularly interesting. But basically, at that time, at any given time, the model gives you a 6 hour ahead prediction, and it's completely based on L1 observation from ACE. That's the reason why you can't really go much further than 6 hours. In fact, I would argue that even better than more than 3 hours, the model isn't really performing very well. Actually, before doing LiveDST, we had a paper which we didn't really manage to put as a live model online. But this is the paper by Andong Wu, postdoc. He was previously with me in Amsterdam, and now he's in Boulder. And this was a probabilistic model that kind of a classification model that estimated the probability that DST went below minus 100 nanotesla. So it's again kind of binary classification, storm / non-storm. But this was done 1 day ahead using images. Might not be very visible here, but this is one example of the test set of this was the Halloween storm of end of October 2003. It's very famous because there's there's two negative peaks. So the blue line here is the DST. It was a very strong storm, minus 400 almost. And the red line is the probability that DST will go below minus 100, and this is predicted 1 day ahead, right? And you can see that from this point on, the probability grows up to, is here up to 1, so almost certainty right before the peak. So it worked very well in this case. Another model which is live on so we have decided to start this kind of franchise with all the live models. Is the live wire, which and this is the paper that came out October 2024. So this is a 1 hour ahead forecast of the horizontal electric field. This is relevant for GIC, geometrically induced current. you might know that whenever there's a storm and the sudden perturbation of the magnetic field is induced an electric current on the ground, which eventually might get discharged on electric conductors like wires. So it's important for the power companies to know in advance when there will be these events. So this is an estimate of the horizontal, the ground electric field. In this case, it was very hard to do already 1 hour ahead, so it doesn't really go much further than that. And on the website, so this is actually just a nowcast. There's an interactive map, which is actually very, very nice. You can. So it's obviously just for the continental US. You can click on any point on the grid, and we'll give you, kind of not visible here, but it will give you the time series of the electric and magnetic field on the ground at that location. All right, moving on. Much time? I think I'm running very much.
Yeah, it's
10:57, up to 10:10. Okay.
15 minutes. Yeah.
Okay. I'm gonna go a bit quicker. Okay, we're working on ambient solar wind velocity. Okay, this maybe I'm gonna skip this, but just to show that the WSA NMIL, which is the operational model at NOAA and UK Met Office, has a really hard time predicting these large jumps, which are not CME induced, but those are CIR, these are correlated interaction regions, even though they look very much like shock lights, so they look like CMEs. So one paper kind of in that direction that it's not yet published, but it's on the archive. It's one of those papers on the archive that might or might not be relevant, by Pratik Mayank, which is a postdoc in Boulder. This is about improving the WSA model, which is one of these basic models that predicts solar wind velocity from magnetograms, kind of optimizing so WSA comes with several three parameters you can tune, and he has done this by meaning of a sort of a neural enhancement of the WSA model. And so this is called WSA Plus, and the code is actually available somewhere on a GitHub. Something which along this line we have been working on, although paper is not being written yet, is a similar approach where we use the GONG synoptic maps. And so the traditional approach would be to feed these into a chain of empirical model, WSA is one of these, and then propagate with a 3D MHD model and get a prediction at ACE. So what we do is very similar. And instead, though, we use a neural network to predict the boundary condition of the solar wind velocity at 0.1 AU, and then propagate, instead of using a 3D MHD, propagate with a simple Burger's equation, which is a nonlinear it's just a ballistic propagation, essentially. Okay, I'm going to skip this for a matter of time. Okay. Another work, I mean, it's kind of changing gears. I mentioned that machine learning can be used as a sort of an accelerator. This is an example not in space physics or space plasma, but in neutral fluid. But I just want to mention this because it's an example where you can derive sort of do a dimensionality reduction of your simulation, in this case, enforcing some physics constraints. So this is the work done by Raffaello Foldes and Raffaele Marino in Lyon, where they introduced this kind of autoencoder that high order statistically informed neural network. So it kind of enforces the high orders of your statistics. I'm gonna just jump a little bit. Okay, so in 2021, there was a true breakthrough in AI and machine learning. Those are two papers with relative 3,000 plus citations. Basically, up to that point, machine learning meant training a neural network, which is a function approximator, right? So it's a way to map inputs to outputs and to mimic a function. Now, with these two works, neural operators were introduced and basically the change is to go from function approximation to functional approximation, which means that instead of just trying to approximate a single function, you approximate an operator. This is much more powerful because it means that you can use an operator for different boundary condition, different initial condition, and so on, without having to retrain your model. While if you just mimic a function with a neural network, like a physics-informed neural network, this is bound to just a single condition. So this is much more general. And so this work has been used a lot in, again, weather prediction, not so much, in fact, not at all, I think, in our field. And I just want to mention a GU talk, for those of you that will go to New Orleans in December, again, by Pratik, who's training a kind of a true surrogate model of an MHD simulation, again, for solar wind plasma prediction. All right. As I mentioned at the very beginning, so kind of again, switching gears once again, there are ways to discover new physics. This, to me, it's kind of the most maybe exciting and interesting application of machine learning. You might have seen some work trying to do symbolic regression, which means kind of literally deriving a closed intelligible formula. That's been working physics-informed neural networks. I know that some of you are working on this problem as well. Again, to me, this is always been the holy grail of plasma physics, kind of bridging a fluid and kinetic description. So if you're not familiar with this, basically what it means is that when you have a kinetic description, meaning solving the Vlasov equation, this is a fully contained description of your system, assuming that the system is a collisionless plasma that contains all possible information, right? But it's very expensive to solve computationally. In fact, it's impossible to think of a space weather model or a magnetospheric model which is fully kinetic. So one has to do an approximation going all the way to a fluid model. Fluid model can be derived exactly from a kinetic model, but it requires a hierarchy of equations, which means that every equation includes the higher order moments, right? And that's what is called the closure problem, because at some point you have to closure this hierarchy by means of an assumption, an equation of state, or something like that. There's been some preliminary work trying to learn that closure by means of a neural network. Just want to advertise work by my PhD student in London, Sam Burles, which presented this in Madrid at the ML Helio, where he's working on a data-driven plasma closure. I mean, at this point, we're still working on the simplest thing you can think of, which is the 1D Landau damping. And for that case, at least the linear Landau damping, it works quite well. You can't really see here, but these are two lines. One is the exact kinetic simulation, and the other one is a fluid simulation with the closure learned via machine learning. Okay, I'm gonna wrap it up really quickly, but I wanna, so again, in this venue of discovering new physics, there was a work that was published maybe 2 or 3 years ago now, in collaboration with Jacob Bornick's group, where basically we tried to solve the electron transport and radiation, but again, kind of the first order approximation is to assume that there's a radial transport, and usually what has been done for the last 20 or 30 years is to assume that the transport is diffusive. So without this term, this would be the standard way of solving that problem, where F is your phase space density. Now, what we try to do is to add a new term, because there are physical reasons for that, to believe that there is an advection term as well. And then we use a physics-informed neural network to basically derive the optimized values for, basically we have 2 free parameters here, the diffusion coefficient and an advection coefficient. And after you kind of turn the crank on the pin, you end up with the optimal values for your 2 coefficients as a function of, in this case, it's just time and space, just a 1D example. The reason I mentioned this is because I believe that up to this point, PIN, physics-informed neural network, is the only method that can solve such a general inverse problem without the need of a priori parameterization of your unknown coefficients, which you usually have to do if you do Monte Carlo simulation of Markov chain Monte Carlo, which is the gold standard to solve inverse problems, is that you need to parameterize somehow your coefficients. Otherwise, your search space is just too large. Another sort of side product of that work is that you can do, or PIN in general, is that you can do automatic event identification. So in this example, and it's kind of hard to understand, to see maybe, but basically, again, this is time and space. And what is shown here as a colored bar is the residual of the partial differential equation that you solve in the physics-informed neural network. So you can see basically it's a way of seeing where in your domain the equation is solved well and where it is not. So in other words, where the assumption of a advection diffusion equation works and where it doesn't. So we have automatically, so where this is a kind of dashed red line are time period for which the approximation of the advection diffusion didn't work very well. And then after identifying this kind of an automatic way, we looked at the literature, and this is a long table. And for most of those events, there were reasons, and there were kind of events studied in the literature, but some of them we didn't find anything. So it might be interesting to look at the data and see if what actually happened there. Okay, I'm going to conclude just by, again, self-referring to my review paper, where at the end of the paper, I set up what I believe were the challenges at that time, and actually I believe that most of these challenges still exist now, and what is the path forward for machine learning in space weather. So there are 6 kind of open problems, which I think the community should really focus on. The first one, which is daunting problem, is the information problem, right? So if we try, for instance, as many people have tried to do a prediction of one single scalar value, like solar wind velocity, a geometric index, or whatever, and you use as an input all of your, for instance, SDO images. So this is an information problem because you want to go from 200 million pixels to one single value. So it's from the machine learning perspective, this is a feature extraction problem, right? Where, how do you extract the important information from this large, extremely large space? The gray box problem is how to, I mean, we don't want to throw away completely the physics, not yet, at least. So how to incorporate our physics sort of pre-knowledge with machine learning, and that's what I like, and many other people like to call the gray box approach. And we show in this paper how we did this for enhancing MHD model running at NOAA Space Weather Prediction Center. The surrogate problem is, in space weather, you don't have one monolithic model. It's always a chain of models, what people call the sun to Earth or sun to man. So which one of those models in this large chain can actually be replaced by machine learning? There's a trade-off, again, between accuracy and speed up, and so on. I already mentioned the uncertainty problem. So this, for me, it's very critical. Every time you do a prediction, you need to be able to predict the uncertainty on top of it and how those uncertainty propagates through your model. And again, if you have a chain of models, how the uncertainty on one model propagates to the next model, and how to avoid that at the end of those propagation, you just have an outcome which has an absolute insane certainty. This is something I've been focusing lately. And again, there is a poster at HU on this new idea I'm working on, which kind of a fancy name, I like to call the influencer-aware dataset distillation. It has to do with the imbalanced dataset. This is a problem that we will always have with space weather. We care about the 0.01% of the events, and we don't really care about everything else. So I really believe that following the usual path that has been successful in AI and machine learning, where more data is better, doesn't really work in our case. We need to work with better data. So what I'm working on is a way of what is called a distillation, where you have this large data set, but you actually train only on a small subset, which is the most informative for your vetting task. And then finally, again, I mentioned this already, the knowledge discovery explainability problem. I mean, at the end of the day, at least some of us are physicists, so we want to understand and explain and increase knowledge. So how you extract knowledge from whatever machine learning model you have. So I think I'm just on time. So those are the 6 problems, which again were mentioned in the review paper, but I think they're still very much open. That really show that machine learning for space weather is kind of the quintessential interdisciplinary field, you need to know a lot or understand the math, the machine learning, the computer science side, physics, and those 6 problems, in my view, they're fundamental to progress in space weather. But I mean, you can apply those in many other areas in AI and in UQ. And then just to conclude, sort of advertisement to JGR machine learning computation. If you have any work which is relevant to that one, to that field, send it to us. Thank you.
Right. Thank you, Enrico. It was very, very interesting. So we have time for questions. Yes, yes. So we start questions in the room. The question.
Thank you very much for your talk. Very nice overview of our field. I was wondering, what do you think about explainable AI? There are various methods from computer vision. Can be, I think, already having some works. What do you think about that?
Okay, and tricky question. It really depends what is your final task. I mean, as many sort of subfield in AI, it is an hype by itself, right? And people have been following this hype as many other hypes. I mean, what as to be understood is, again, what is important is the final task. If you're, because explainability comes at the cost of accuracy always, right? So if you're really focused on having a model that is the best forecast ever, you might not care too much about explainability in the sense of, I mean, typical explainability means that you want to either understand what inputs are the most important, or even in case of symbolic regression, have a closed formula that you can look at and say, okay, this term means this and this term means that. The neural network, I mean, trying to explain a neural network, especially a deep neural network, is almost impossible. So it really depends, as I said, what your task is. In the example that I mentioned on using PIN for radiation belt, we sort of did that explainability exercise where at the end of the day, we tried, after we trained the model and so on, we tried to see whether those diffusion coefficient and advection coefficient could be parameterized in a simple way. And we, in the paper, we end up with simple cubic fit. And that's sort of a step back to be explainable.
Okay, other questions? Yeah, Wiki?
What would you think a better data set would look like? Like what types of things would you extract for the too often too quiet problem?
So what is the sort of the distillation philosophy or focus? Yeah, that's a tricky one. So again, depends what your task is. So for instance, the way I'm applying this, and again, this is work in progress, is for the DST geometric index prediction, which, I mean, the way I see it's all kind of our playground where things are relatively easy. In that example, obviously, you want to have informative example of storms, right? Maybe not necessarily you want to have also some, but that's again where the algorithm comes into play to decide how much storm versus non-storm you want to have. And typically, I mean, the way to tackle imbalanced problems has been very simple and naive in a sense, either oversampling one category or weighting differently in the cost function, which I'm not saying that those methods don't work, but they might not be optimal because there's no principled way to choose how you do these things, right? So, and typically people just try, and it's a trial and error exercise. So, okay, let's resample this category a bit more. And I mean, most of the work in balanced data set has been done for classification because it's easier, right? We have, say, 2 classes, and one is the majority and one is minority, and you resample. In regression is much harder. So I don't have a final answer for you, but yeah, it's something we're working on.
Yeah, perhaps a follow-up to this question is so if you are trying to fit CRPS, then I guess you're getting this regression to the mean, right? But if you care about extreme events, then you need other scores, I suppose, to evaluate the performance of your algorithm. So what would you suggest we should use? How should we evaluate the goodness of our machine learning models, especially as we benchmark different methods?
Yeah, that's a good question. I think it boils down, I mean, it was kind of hidden somewhere in the slides where I mentioned, it's problematic for defining meaningful metrics, right? What I mean here is that, again, for the balanced data set, that's kind of maybe a sin we've been guilty, all of us have been guilty of, is to, you write a paper and you show the root mean square error and say, oh, this is great because it's better than this other paper. But the root mean square error is, it's global, averages everything. So we need to come up with, so what me and Andong like to do in some of our paper is to do, for instance, RMSE condition on values. So you, instead of just one single value, you show like a curve of how that error depends on the target value. So I think there's no, I mean, some work has been done, needs to be done in that respect as well to come up with, as usual, there's never going to be one single metric that covers it all, right? It's, again, as if you look at classification, there's always these 5-6 different metrics you want to compute, and it's the same here. But yeah, you need to, look at what in extreme events, or for instance, in the case of solar wind speed prediction, you define a threshold on how many times you capture the high speed streams and so on. So again, I don't have definite answer for you, but it's definitely a work that needs to be done to come up with better metrics.
Okay, so other questions in the room?
Are there any questions online?
Yeah, perhaps from the online participants.
I want them to raise their hand.
You can raise your hand and you can unmute and you can have any questions.
There might be someone in the waiting room. I've seen the pop. Have you accepted all the people?
I was hoping that someone was admitted, because then I was able to change the slides.
Yeah, there was a bunch of people that were.
Yeah, but I think they were admitted in the end. No?
Like whom?
No,
Other
Carla
people
was
there.
not on that. No. Carla is still in the waiting room.
Can you check the waiting room?
Yeah. There's everyone's here.
Yes, I see Carla. She was the last one to join. Thanks, Aidan. Thank you. Okay, no questions in the chat.
Yeah. All right. Okay, then thanks a lot. That was really interesting talk.
Thank you.